Most of the universe is missing from sight. Every star, planet, ocean, mountain, and living cell belongs to less than 5% of cosmic reality. The rest is hidden dark matter quietly holding galaxies together, and dark energy stretching the universe faster with every passing age. Nothing about them can be touched or seen directly, yet their fingerprints are written across rotating stars, bent light, distant supernovae, and the vast structure of space itself. Somewhere between gravity and emptiness, the universe is revealing that everything familiar may be only a thin, luminous surface over something far stranger. Thank you for spending this time here. Share in the comments what time it is where you are listening, and which part of the world is beneath your night sky. A like helps this journey reach more curious minds. A subscription keeps future explorations close, and sharing the video may bring someone else into the mystery. Now, let the visible universe fade gently into the background and enter the hidden cosmos. Everything familiar begins with ordinary matter. It forms the air around a planet, the stone beneath a mountain, the water inside an ocean, and the cells within every living body. It gathers into dust, ice, clouds, moons, worlds, stars, and the vast glowing cities of stars called galaxies. At the smallest scales, this matter is built from atoms, and atoms are shaped by particles such as protons, neutrons, and electrons. These ingredients create nearly every object that can be touched, measured directly, photographed, or placed inside a laboratory. They fill the visible world so completely that reality appears to be made almost entirely from them. Yet when the universe is measured as a whole, this entire familiar inventory becomes a thin minority. Ordinary matter accounts for less than 1/20th of the cosmic total. Everything that shines, everything that reflects light, and everything that has ever been known through direct experience belongs to this narrow fraction. The remaining universe is dominated by two unseen components. Roughly a quarter behaves like hidden matter, while most of the rest behaves like an unknown form of energy associated with the expansion of space. These names, dark matter and dark energy, sound descriptive, but they are really signs of ignorance. Dark does not simply mean black, it means unseen, unmeasured in any direct way, and known mainly through effects that appear across enormous distances. The familiar universe is therefore not the whole structure, but only its illuminated surface. Stars create nearly all the light that reveals distant galaxies, yet the stars themselves seem to trace only a small part of the mass around them. Planets may be common, dust may drift between solar systems, and immense clouds of gas may lie between stars. But even all of these combined are not enough to explain the way the cosmos is built. The scale of the mismatch is difficult to absorb because ordinary matter defines every daily instinct. Weight, shape, heat, color, pressure, motion, and touch all arise from interactions involving familiar particles. Human senses are tuned to the behavior of this visible fraction. Eyes respond to light. Skin responds to electromagnetic forces between atoms. Instruments extend these senses, detecting wavelengths too long or too short for vision, particles too small to see, and signals too weak to feel. Even so, these tools mostly explore the same family of matter. They reveal more detail within the visible fraction, but they do not automatically expose the hidden majority. The strange result is that the universe can be well observed and still remain largely unknown. A telescope may record billions of galaxies, each containing billions of stars, and still be looking at only the bright decoration of a much larger structure. The mystery grows from a simple comparison between what is seen and what is required. Visible matter has gravity. Every star pulls on every other object. Every galaxy attracts nearby galaxies. Over time, gravity gathers diffused material into denser regions, allowing stars and galaxies to form. But when astronomers calculate how much gravity the visible material should produce, the answer is too small. The stars move too quickly. Galaxies remain bound when their visible mass suggests that they should come apart. Clusters of galaxies hold together with a strength that the glowing matter cannot explain. The first hint of the hidden universe is therefore not a new object appearing in an image. It is a failure of the visible universe to behave as expected. Something seems to add gravity without adding light. This missing influence does not appear in a single isolated place. It appears again and again. From the motion of stars inside galaxies to the growth of the largest structures in the cosmos, the pattern is too broad to dismiss as a local error. Ordinary matter alone does not seem capable of building the universe that exists. Without an additional source of gravity, the early cosmos would struggle to gather material efficiently enough to create the complex web of galaxies seen today. The visible stars would be more scattered, the great clusters would be less stable, and the large filaments of matter-spanning cosmic space would be harder to form. Dark matter enters the picture as the unseen framework that gives ordinary matter deeper gravitational wells in which to collect. It does not replace atoms. It doesn't form glowing surfaces, oceans, rocks, or bodies. Instead, it appears to surround galaxies in vast diffuse halos, extending far beyond the regions where most stars are found. In this sense, every bright galaxy may be only the inner visible core of a much larger invisible structure. The light marks where ordinary matter has cooled, collapsed, and ignited, while the dark component provides much of the gravity shaping the system. This is why the 5% is not merely a statistic. It changes the meaning of every astronomical image. A spiral galaxy may look complete, with its bright central bulge and winding arms, but the image captures only the matter that interacts strongly with light. The greater mass may be spread around it in a form that neither shines nor casts a conventional shadow. A cluster of galaxies may look like a collection of luminous islands, yet most of the gravitating material may lie between and around those islands. Even the apparent emptiness between cosmic structures may contain influences that cannot be seen directly. The universe becomes a place where visibility and importance are no longer the same. What shines is not necessarily what dominates. What can be touched is not necessarily what shapes the larger scales. The other great hidden component deepens the imbalance even further. Dark energy does not behave like matter gathered into halos or clusters. Instead, it is linked to the expansion of space itself. On sufficiently large scales, galaxies are moving away from one another as the universe expands. More surprisingly, that expansion is accelerating. Gravity from matter should act as a brake, slowing the growth of cosmic distances. Yet observations indicate that the opposite trend dominates at late times. Some unknown effect is causing expansion to speed up. This effect is given the name dark energy, but the name does not reveal its nature. It may be a property of empty space, a constant energy built into the structure of the cosmos, or something more dynamic that changes over time. Whatever it is, it appears to account for most of the cosmic energy budget. The result is a universe in which atoms are both essential and secondary. They are essential because they form stars, chemistry, planets, and life. They create every observer, every instrument, and every measured signal. Yet they are secondary because they do not provide most of the mass and energy governing the universe. The familiar world is not false, but it is incomplete. It is a bright island within a deeper system whose main components remain hidden. This creates an unusual scientific situation. Dark matter and dark energy are not minor corrections added to an otherwise finished picture. Together they form the majority of the picture. Modern cosmology can describe many of their effects with remarkable precision, but the underlying substances remain unknown. Their existence is inferred through patterns in motion, light, structure, and expansion. They are known by what they cause rather than by what they are. Even the language of darkness reflects this distance. It names a boundary in present knowledge, not a final explanation. Each measurement sharpens the outline of the unseen while leaving its inner nature concealed. Science can map where the effects gather, estimate how strongly they act, and follow their influence across cosmic history. Yet the central identities remain beyond direct reach. The visible 5% therefore stands at the center of a quiet reversal. For most of history, the stars seemed distant and mysterious, while the material world seemed immediate and secure. Now the stars, planets, and bodies of ordinary experience are understood as variations of the same atomic substance, while the larger universe is recognized as something stranger. The known world becomes the exception rather than the rule. Every atom carries a history reaching back to the early universe, yet all atoms together form only a thin layer of cosmic reality. Beyond that layer lies the gravity of unseen mass and the pressure of an unseen energy. The hidden universe does not announce itself with color or sound. It reveals itself through absence, imbalance, and motion. It becomes visible only when the familiar universe fails to explain itself. And in that failure, the cosmos begins to open into a mystery far larger than the light it contains. A galaxy appears to be a settled thing, a great wheel or cloud of stars turning through space under the quiet rule of gravity. Its shape can endure for billions of years. Spiral arms curve around bright central regions. Old stars gather in rounded halos, and clouds of gas drift between them. At first glance, the explanation seems simple. Each star pulls on every other star, and the combined attraction holds the system together. Yet when the motions inside galaxies are measured, the visible matter does not provide enough gravity. The problem reaches into the basic balance between speed and mass. An object moving in a circle needs an inward pull to keep it from flying away. The faster it moves, the stronger that pull must be. In a galaxy, stars far from the center travel around the galactic core at unexpectedly high speeds. If most of the mass were concentrated where most of the light is seen, those outer stars should move more slowly than stars closer in. This is the pattern found in the solar system, where distant planets orbit more slowly because most of the mass lies in the sun. Galaxies do not follow that decline. Their outer stars often maintain nearly constant orbital speeds across enormous distances. The visible disk becomes faint, but the gravitational influence does not fade as quickly as expected. The galaxy behaves as though it contains far more mass than its stars and gas can account for. This discrepancy is expressed through what astronomers call a rotation curve, a graph showing orbital speed at different distances from a galactic center. The expected curve falls as visible matter becomes sparse. The observed curve often remains flat. That flatness is one of the clearest signs that an unseen component surrounds the luminous galaxy. The extra mass cannot be packed only into the bright center, because the orbital pattern requires it to extend far outward. The usual interpretation is a vast halo of dark matter, roughly spherical and much larger than the visible disk. The stars move inside this halo as leaves might drift within a deep invisible current. The glowing structure captured in a telescope is only the inner region, where ordinary matter has become dense enough to form stars. Beyond the last visible arms, the gravitational system continues through a diffuse envelope of unseen mass. The halo is not a solid shell. It is a distribution of matter whose combined gravity shapes the paths of stars, gas clouds, satellite galaxies, and streams of stellar debris. The evidence becomes stronger when many kinds of motion tell the same story. Small companion galaxies orbit larger ones at speeds that imply additional mass. Long streams of stars trace the gravitational field through which they move. Gas beyond the bright stellar disk follows paths that visible matter cannot explain. In elliptical galaxies, where stars travel in many directions rather than along a neat disk. Their velocity patterns also indicate hidden mass. The missing mass also appears on scales larger than individual galaxies. Galaxies gather into clusters containing hundreds or thousands of members. These clusters are bound systems with galaxies moving through them at great speed. When the visible stars and hot gas are added together, the total mass still falls short of what is needed to keep the cluster intact. The galaxy should escape, yet the cluster remains. In many clusters, most ordinary matter is not locked inside stars. It exists as extremely hot gas spread through the space between galaxies. This gas can be detected because it emits high-energy radiation, but even after it is measured, the gravitational account remains incomplete. The unseen component outweighs both the stars and the gas, binding the whole system into a single structure. The same conclusion emerges from the way clusters affect background light. Their gravity bends the paths of light passing nearby, creating arcs, distortions, and repeated images of more distant galaxies. The amount of bending reveals the total mass along the line of sight. Again, the mass inferred from gravity exceeds the mass that can be seen. The invisible component is not added merely to repair one awkward calculation. Orbital speeds, cluster dynamics, hot gas, and distorted light all point toward the same missing substance. The evidence also reaches backward into cosmic history. The early universe begins in an almost uniform state, with only tiny variations in density. Over time, gravity amplifies these variations. Regions with slightly more matter pull in additional material and become denser. Eventually they form the seeds of galaxies, clusters, and the vast web of structure spread across the observable cosmos. Ordinary matter alone struggles to build this structure quickly enough. In the early universe, atoms are strongly influenced by radiation before neutral atoms form. Ordinary matter exists as a hot charged plasma that cannot collapse freely, because light pushes and scatters through it. A dark component that does not interact strongly with radiation can begin gathering earlier. It forms gravitational wells before ordinary matter is free to fall into them. Once atoms form and light travels more easily, gas settles into these pre-existing wells, where stars and galaxies can develop. Dark matter therefore acts not only as hidden mass around mature galaxies, but as an early framework for cosmic growth. Without it, the universe would have difficulty producing the richness and organization now observed. Simulations of structure formation reinforce this idea. When a large amount of cold, slow, moving dark matter is included, gravity builds a network of dense knots connected by long filaments. Galaxies form along these filaments and gather in clusters at their intersections. Vast underdense regions open between them. This pattern resembles the cosmic web mapped by surveys of distant galaxies. The agreement is not perfect in every detail, and the behavior of dark matter on smaller scales remains under study, but the broad structure is difficult to explain without a dominant unseen mass. The word cold in this context does not mainly describe temperature. It means that the particles move slowly enough in the early universe to gather into relatively small structures rather than washing them away through rapid motion. Dark matter halos grow and combine, while ordinary gas inside them cools and ignites into stars. The visible universe develops within an invisible architecture. Yet the concept remains strange because the mass seems both abundant and elusive. It exerts gravity over enormous distances, but it does not appear to emit, absorb, or reflect light in the usual way. It passes through the luminous regions of galaxies without settling into disks like gas. Ordinary matter can lose energy through collisions and radiation, allowing it to collapse into dense stars and planets. Dark matter seems unable to cool in the same manner. It stays spread through broad halos, surrounding the denser structures made from atoms. This difference explains why a galaxy can contain a thin, bright disk inside a much larger rounded dark halo. The unseen mass is also not simply a convenient name for every uncertainty in astronomy. Visible matter is measured through many channels, and gravity is tested across a wide range of conditions. Errors exist, but the missing mass appears too consistently to disappear through a small correction. Some alternative theories propose that gravity itself behaves differently on galactic scales, reducing the need for dark matter in certain situations. These ideas can reproduce some observed patterns, especially the relation between visible matter and rotation in many galaxies. Yet they face difficulties when applied to galaxy clusters, gravitational lensing, early cosmic structure, and the history of expansion. The debate tests whether the mystery lies in an unknown substance or in an incomplete theory of gravity. Still, the dominant framework treats dark matter as real matter whose nature has not yet been identified. This framework succeeds because the same assumption explains a wide range of otherwise disconnected observations. The missing mass becomes visible through consistency. It appears wherever gravity is stronger than light predicts, wherever structures form more efficiently than atoms alone allow, and wherever galaxies move as though held inside something larger than their luminous bodies. A galaxy is therefore not merely a collection of stars. It is a bright concentration embedded within an unseen gravitational landscape. The stars reveal the inner pattern, but the deeper structure is traced by their motion. Their speed becomes a kind of testimony. Each orbit records the pull of matter that cannot be photographed. Each cluster records a hidden weight. Each filament of the cosmic web suggests an ancient framework laid down before the first stars began to shine. The universe does not hide this mass completely. It hides its appearance, but not its consequences. Gravity carries the message across darkness, and the message is repeated on every scale. The visible cosmos is not massive enough to explain the form it has taken. A galaxy reveals its hidden mass through motion long before that mass can be identified. Light provides the measurement, but gravity writes the pattern. Every star and cloud of gas moves through a shared gravitational field, and each motion carries information about the amount and distribution of matter creating that field. Astronomers cannot follow a single star around an entire galaxy, because one orbit may take hundreds of millions of years. But they do not need to wait. The speed of a star can be inferred from the way its light shifts in wavelength. Motion toward an observer compresses the light slightly toward the blue end of the spectrum, while motion away stretches it toward the red. Across a rotating galaxy, one side tends to approach and the other tends to recede. By comparing these shifts at different distances from the center, the rotation of the galaxy can be mapped. The result is not a simple spinning wheel. Stars closer to the center and stars far into the faint outer regions follow different paths, yet their speeds form a pattern that repeatedly points beyond the visible material. In a system where nearly all mass is concentrated near the center, orbital speed should decline with distance. The solar system provides a familiar example. Mercury moves around the Sun more quickly than Earth, and the outer planets move more slowly still. The Sun contains almost all the system's mass, so its gravitational pull weakens with distance in a predictable way. A galaxy contains mass throughout its disk rather than at a single central point, so the comparison is not exact, but the expectation remains similar. Beyond the bright region holding most of the stars, orbital speeds should begin to fall. Instead, in many spiral galaxies, the curve stays nearly flat. Hydrogen gas far outside the luminous disk often circles at almost the same speed as material much closer to the center. The visible mass thins out, but the gravitational influence remains strong. To sustain those outer orbits, additional mass must continue accumulating with distance. The farther the measurement extends, the more unseen matter the galaxy appears to contain. This is one reason dark matter is pictured as a broad halo rather than a compact object. A concentrated mass at the center would produce the wrong pattern. The hidden material must extend around and beyond the stars, contributing gravity throughout a region much larger than the visible galaxy. Different galaxies display different details, but the basic discrepancy appears with remarkable persistence. Massive spirals, modest disk galaxies, and many small dwarf systems all move as though immersed in unseen gravitational envelopes. Some dwarf galaxies contain relatively few stars yet show very large internal motions, implying that dark matter may outweigh their visible material by an especially large amount. In such systems, the luminous component is only a faint tracer moving inside a dominant dark structure. Other small galaxies appear to contain less dark matter than expected, reminding astronomy that the relationship between visible and invisible matter is not perfectly uniform. These unusual cases are valuable because they test how galaxies form, lose material, and interact with their surroundings. They do not erase the wider evidence. Instead, they reveal that dark matter halos can be reshaped by collisions, tidal forces, and the long history of galactic growth. Motion inside elliptical galaxies tells the same story in a less orderly form. These galaxies do not contain thin rotating disks with clearly defined spiral arms. Their stars move along many crossing orbits, creating a rounded or stretched body of light. Rather than measuring a single rotation speed, astronomers study velocity dispersion, the spread of stellar speeds within a region. If the stars move rapidly in many directions, a strong gravitational field is required to keep them bound. The visible stars provide part of that field, but in the outer regions the measured motions often imply additional mass. Hot gas surrounding giant elliptical galaxies offers another clue. The gas reaches temperatures so high that it emits energetic radiation. Without a deep gravitational well, it would escape into intergalactic space. Its continued presence indicates that the galaxy is more massive than starlight alone suggests. The Milky Way carries similar evidence close to home. The Sun and nearby stars orbit the galactic center within a broad disk, while globular clusters, satellite galaxies, and distant stars move through the larger galactic halo. Their paths help estimate how much mass lies beyond the bright band visible from Earth. The result suggests that most of the Milky Way's mass is not contained in its central bulge, spiral arms, gas clouds, or stars. The visible galaxy is embedded in a much larger dark halo. Its outer boundary is not sharp. The density of dark matter gradually decreases with distance, blending into the wider environment of nearby galaxies. The halo may extend several times farther than the stellar disk, shaping the motion of objects that seem almost detached from the galaxy's light. Streams of stars provide especially delicate probes. These long, narrow ribbons form when a small star cluster or dwarf galaxy is pulled apart by tidal forces. As the disrupted system orbits, its stars spread along a common path, tracing the gravitational field through which they travel. A smooth, simple halo produces one kind of stream. A lumpy halo filled with smaller concentrations of dark matter can disturb the stream, opening gaps or bending its course. By studying these fragile structures, Astronomers can search not only for the total dark mass, but also for the way it is distributed. A passing dark clump may leave no flash and emit no radiation, yet its gravity can disturb a stellar stream like an unseen stone sending ripples through calm water. Galactic bars and spiral patterns add further complexity. Stars in a galaxy do not all move independently through a fixed background. Their collective gravity creates waves, resonances, and long-lived structures. Gas responds differently from stars because it can collide, cool, and form new stars. Dark matter, if it interacts mainly through gravity, does not easily lose energy in the same way. It remains in a broad halo while ordinary matter settles into a rotating disk. The two components influence one another over cosmic time. A growing disk can alter the inner shape of the halo, while the halo can slow a rotating bar by exchanging angular momentum with it. Exploding stars and bursts of star formation can push gas out of small galaxies, causing the gravitational center to fluctuate and perhaps changing the density of dark matter near the core. These processes make the interpretation of galactic motion more difficult, but they also make it richer. Dark matter is not merely an invisible weight added after the galaxy forms. It participates gravitationally in the galaxy's entire history. The measured relation between visible matter and orbital speed is therefore both orderly and puzzling. Galaxies with more ordinary matter generally rotate faster, and the distribution of stars and gas often predicts details in the rotation curve. This close connection raises an important question. If dark matter is a separate substance spread through halos, why does its gravitational effect so often track the visible matter so closely? This standard picture answers that both components grow together under gravity and influence each other during galaxy formation. Alternative ideas argue that the pattern may point to a change in the laws of gravity at very low accelerations. Such theories can describe some galactic rotation curves with impressive accuracy, especially when visible matter is carefully mapped. Yet a successful explanation must also account for galaxy clusters, gravitational lensing, the cosmic background, and the growth of large-scale structure. Galactic motion is therefore not only evidence for missing mass, it is a testing ground where different descriptions of the universe compete. The strongest interpretation is not chosen from one curve or one galaxy, but from the combined pattern across many scales. Measurements of stars, gas, satellite systems, stellar streams, and entire clusters repeatedly reveal more gravity than visible matter can supply. The hidden mass behaves consistently enough to map, but not clearly enough to identify. Its presence is inferred from speed, from confinement, and from the endurance of structures that would otherwise disperse. Each galaxy becomes a natural instrument. Its stars serve as test particles. Its gas traces distant orbits. Its faint companions mark the reach of the halo. The galaxy's own motion reveals the architecture surrounding it. There is no single photograph of dark matter, yet there are countless records of its pull. The mystery remains quiet because nothing visibly moves in an impossible way. The stars simply follow their paths. Only when those paths are compared with the mass that shines does the hidden universe become unavoidable. The motion is smooth, the equations are familiar, and the conclusion is strange. Around nearly every luminous galaxy lies a much larger domain, whose gravity is evident and whose substance remains unknown. Light seems to travel in straight lines, yet across the universe even light must follow the shape of space. Massive objects curve the space around them, and a beam passing through that curvature is deflected from the path it would otherwise take. This effect, called gravitational lensing, allows invisible matter to reveal itself without emitting a single photon. a foreground galaxy or cluster can act like a vast natural lens, bending the light of objects far behind it. The lens is not made of glass, and the bending does not come from reflection or refraction. It comes from gravity altering the geometry through which light moves. The greater the mass, the stronger the distortion. This makes lensing a direct way to measure total mass, whether that mass is bright, faint, or completely dark. When the alignment between a distant source, a massive foreground object, and an observer is especially precise, the background light may be stretched into arcs or even a nearly complete ring. In less perfect alignments, the source may appear more than once, producing several images of the same galaxy or quasar around the foreground mass. These patterns are not random decorations. Their positions, shapes, and brightness carry information about the lensing mass. By working backward from the distorted image, astronomers can reconstruct the gravitational field that bends the light. The method does not require assumptions about whether the mass is made of stars, gas, dust, or an unknown particle. Gravity treats all mass alike. For this reason, lensing is among the most powerful tools for tracing dark matter. A cluster of galaxies may contain hundreds of luminous members and vast clouds of hot gas. Yet the visible material does not account for the full lensing signal. The arcs around the cluster curve more strongly than the bright matter alone can explain. The missing gravitational influence appears to be spread through a broad halo surrounding the entire system. In detailed maps, dark matter often forms the main framework, while the galaxies and gas occupy smaller regions within it. The cluster becomes a layered structure in which most of the mass cannot be seen directly, but its outline is written into the light of far more distant objects. Strong lensing creates the most dramatic examples, but it occurs only when the geometry is favorable. A quieter form, called weak lensing, is far more common. In weak lensing, individual background galaxies are distorted only slightly. Their shapes may be stretched by an amount too small to notice in a single image. Yet when thousands or millions of galaxies are studied together, a statistical pattern emerges. Their apparent orientations become subtly aligned by the gravitational fields along the line of sight. From this collective distortion, astronomers create maps of mass across enormous regions of the sky. These maps reveal concentrations of matter that do not always match the distribution of visible light. Dense areas of dark matter appear where many galaxies gather, but the dark structure can extend beyond the luminous boundaries and connect clusters through broad filaments. In this way, weak lensing traces the cosmic web itself. The method is delicate because galaxies possess their own shapes before lensing occurs. Spiral galaxies may already be elongated, irregular, or tilted. Atmospheric blurring, telescope optics, and detector effects can also alter an image. To isolate the gravitational signal, surveys must measure these distortions with extraordinary care and compare vast populations. The true lensing pattern is small, but it is coherent across the sky. Random galactic shapes average away, while the shared gravitational distortion remains. The result is not a photograph of dark matter in the ordinary sense. It is a reconstruction, built from the repeated bending of distant light. Still, it is one of the closest approaches to seeing the invisible. The most striking demonstrations come from collisions between galaxy clusters. Clusters contain galaxies, hot gas, and dark matter, and these components behave differently when two clusters pass through one another. The galaxies are widely separated, so they usually move through the collision with few direct impacts. Dark matter, if it interacts mainly through gravity, should also pass through with little resistance. The hot gas behaves differently. gas particles collide, create pressure, slow down, and heat further. As a result, the gas can be left behind between the separating clusters while the galaxies continue onward. Observations of such systems show that the strongest lensing mass often remains aligned with the galaxies rather than with the slowed gas. This separation matters because the hot gas contains most of the ordinary matter in a cluster. If ordinary matter alone were responsible for the gravitational field, the lensing signal should remain centered on the gas. Instead, much of the mass appears to pass through the collision along with the galaxies. The pattern supports the idea of an additional component that does not collide strongly with ordinary matter. It also places limits on how strongly dark matter may interact with itself. If dark matter particles collided often, their distribution would slow and spread during cluster mergers. The fact that the lensing mass can remain relatively compact suggests that any such interactions are weak, at least under these conditions. Lensing also reaches down to the scale of individual galaxies. A foreground galaxy can produce several images of a distant quasar, a brilliant region powered by a feeding black hole. Because the light in each image follows a different path, it travels a different distance and passes through a different depth of curved space. If the quasar changes in brightness, the variation appears in the separate images at different times. These delays allow astronomers to study the mass distribution of the lensing galaxy, and can also provide information about cosmic expansion. Small clumps of dark matter inside the galaxy may alter the brightness or position of the images. Such effects offer a way to search for dark structures that contain few or no stars. The number and size of these clumps can help distinguish between different dark matter models. Some candidate particles would create many small halos. Others would erase the smallest structures in the early universe, producing smoother distributions. Lensing therefore does more than confirm that unseen mass exists. It begins to test what that mass might be like. Another form, called microlensing, occurs when a compact object passes in front of a background star. The foreground object may be too faint to see, but its gravity temporarily magnifies the distant star. The star brightens and later returns to normal as the alignment changes. Microlensing surveys have searched for dark compact objects such as faint stars, wandering planets, or black holes that might account for the missing mass around galaxies. These searches show that some invisible ordinary objects exist, but they do not appear numerous enough across the required mass ranges to explain all dark matter. The halo cannot be made mainly from hidden stars or familiar compact remnants. Lensing closes another path and pushes the mystery toward a more unfamiliar substance. Yet the interpretation is never entirely simple. A lensing map records all mass projected along the line of sight. Structures at different distances can overlap, and turning the distortion into a three-dimensional picture requires additional measurements. The visible gas and stars must also be mapped carefully before the dark component can be separated from them. Even so, the broad result remains stable. Wherever gravity bends light more strongly than visible matter predicts, an unseen mass is required or the theory of gravity must change. The same choice appears in galactic motion, but lensing tests it through a different phenomenon. Rotation curves depend on how objects move within a gravitational field. Lensing depends on how light crosses that field. The agreement between the two strengthens the case that the discrepancy is real. Light becomes a messenger from behind the hidden mass. It passes through regions that cannot be illuminated directly, and arrives carrying the imprint of their gravity. A stretched arc marks the shape of a cluster's mass. A repeated quasar reveals the depth of a galactic potential. A faint alignment among countless background galaxies outlines the web of matter across cosmic space. None of these images shows the dark substance itself. They show what space becomes in its presence. This is the quiet power of gravitational lensing. The invisible does not need to shine. It only needs to bend the path of something that does, across billions of light years. Distant galaxies provide the background, gravity provides the lens, and dark matter leaves a visible signature in the geometry of light. Dark matter is known first by what it does, but almost as importantly by what it fails to do. It adds gravity to galaxies and clusters, yet it does not shine like stars, glow like hot gas, block light like dense dust, or reveal itself through the usual signatures of ordinary matter. The hidden mass cannot simply be ordinary matter placed where telescopes have not looked. Ordinary matter interacts with light and with itself in ways that leave traces. Gas can absorb and emit radiation. Dust dims and reddens background stars. Cold clouds can reveal themselves through radio signals, heating, motion, or the way they affect nearby material. Faint stars produce at least a little light. Dead stars, planets, and compact remnants bend and magnify background light when they cross a line of sight. A universe filled with enough ordinary objects to explain dark matter would not remain silent. It would alter the chemistry of the cosmos, the pattern of ancient light, and the formation of stars in ways that do not match observation. The problem begins with the early universe. In its first minutes, conditions are hot and dense enough for the simplest atomic nuclei to form. The proportions of hydrogen, helium, and small amounts of other light elements depend on how much ordinary matter exists at that time. Later measurements of these elements agree with a universe containing far less ordinary matter than the total amount required by gravity. A second record appears in the cosmic microwave background, the faint afterglow released when the early universe becomes transparent. Tiny variations in this radiation preserve information about the balance between ordinary matter, dark matter, and radiation. The pattern again indicates that most gravitating matter is not made from protons and neutrons. Dark matter therefore cannot be a hidden warehouse of the same substance that forms stars, planets, gas, and bodies. The total supply of ordinary matter is already counted, even when much of it is difficult to see. Some of that ordinary matter is indeed dark in the everyday sense. Cold gas drifts between galaxies. Dust clouds obscure distant light. Small stars burn dimly. Rogue planets move without parent suns. Black holes absorb light once it crosses their boundaries. Yet all these objects belong to the known atomic inventory, and together they cannot account for the missing mass. Their abundance is limited by early cosmic chemistry, background radiation, and direct searches. Invisible matter is not automatically dark matter. A cold planet in interstellar space may be invisible to an ordinary telescope, but it still reflects, emits, absorbs, and gravitationally lenses light according to familiar physics. Dark matter appears to belong to a different category. It is not merely hard to see, it seems largely indifferent to light. Antimatter offers another tempting possibility because it sounds exotic and can remain invisible at a distance. Antimatter particles have the same mass as ordinary particles, but carry opposite charges and related quantum properties. When matter and antimatter meet, they can annihilate, converting much of their mass into energetic radiation. If galactic halos were made primarily from antimatter, their boundaries with ordinary gas would become bright in characteristic gamma rays. Galaxies moving through antimatter environments would generate widespread signs of annihilation. Such signals are not seen at the level required. Antimatter may exist in limited amounts through natural particle processes, but it cannot quietly fill the halos of ordinary galaxies without revealing violent contact zones. It follows from the energetic consequences that would accompany it. Neutrinos provide a subtler candidate. These extremely light particles are real, abundant, and difficult to detect. They pass through ordinary matter with almost no interaction, and vast numbers cross planets and bodies continuously without leaving noticeable effects. For a time, their ghost-like behavior makes them seem suited to dark matter. Yet known neutrinos move too quickly in the early universe. Fast particles stream out of small regions before gravity can bind them, smoothing away the density variations needed to build galaxies. A universe dominated by such hot dark matter would form large structures first and smaller ones later, producing a pattern unlike the observed cosmic web. Galaxies and small halos appear too early and too numerous. No neutrinos contribute some mass to the universe, but not enough, and their motion makes them unsuitable as the main hidden framework. Any successful dark matter particle must behave more slowly during the era when structure begins to grow, allowing small gravitational clumps to survive. Black holes create one of the most persistent alternatives because they are massive, dark, and governed by gravity. A black hole emits no ordinary light from within its event horizon, and an isolated one may drift almost unnoticed. It might seem natural to imagine vast numbers of them scattered through galactic halos. Some black holes certainly contribute to the dark mass budget, just as faint stars and planets do. Searches for gravitational microlensing place strong limits on many possible black hole masses. If halos contained enormous populations of compact objects, they would frequently pass in front of background stars and temporarily magnify them. Surveys observe such events, but not often enough across broad mass ranges to account for the full halo. Other constraints arise from the way black holes would affect star clusters, binary systems, background radiation, and the distribution of matter in galaxies. Very small black holes would face additional limits from evaporation and high-energy emission, while large populations of massive black holes would disturb their surroundings too strongly. A narrow range of primordial black hole masses may still provide some fraction of dark matter, and the exact limits remain an active subject of research. Yet ordinary stellar black holes and known compact remnants cannot explain the dominant component. They are too concentrated, too detectable through their effects, and too closely tied to the limited amount of ordinary matter from which stars form. Dust and cold molecular clouds fail for related reasons. Enough hidden gas to account for galactic halos would collide, cool, and gradually settle toward disks. It would form stars or produce radiation as it changed temperature and density. It would absorb light from distant objects and alter the appearance of galaxies. Dark matter does not show this dissipative behavior. During collisions between galaxy clusters, the hot ordinary gas slows because its particles interact, while most of the gravitational mass passes onward with the galaxies. The separation suggests that the dominant hidden component does not experience strong drag. It behaves as though its particles move through one another and through ordinary matter with little resistance. This property prevents dark matter from collapsing into thin disks, dense clouds, or stars. Gravity gathers it, but without efficient ways to shed energy. It remains spread through large halos. The absence of collision signals therefore becomes another clue. Dark matter is not only non-luminous, it is weakly collisional. It does not seem to carry ordinary electric charge, because charged particles would scatter light, interact with magnetic fields, and couple to hot plasma. It cannot be made mainly from familiar atomic nuclei, because those nuclei would participate in nuclear reactions and leave records in early element abundances. It cannot be a diffuse sea of ordinary objects, because their lensing and radiation would be measurable. Each exclusion sharpens a strange profile, abundant, massive, gravitationally active, electrically neutral, stable across cosmic time, and nearly transparent to both light and matter. Still, ruling out candidates does not reveal the answer automatically. Science often advances by narrowing a field of possibilities until only unfamiliar territory remains. Dark matter occupies that territory. It may consist of a new particle or family of particles beyond the current standard description of nature. It may include more than one component. It may interact through forces that ordinary instruments barely sense. It may even expose a deeper modification in the understanding of gravity. Although such alternatives must reproduce the many successes of the particle picture across cosmic history, they show that the missing mass is unlikely to be a misplaced form of something already known. The universe is not hiding dark matter behind a cloud or inside a convenient population of dead stars. It is hiding it behind a lack of interaction. Familiar matter announces itself through heat, light, pressure, collision, chemistry, and radiation. Dark matter withholds nearly all of these signs. What remains is gravity, persistent and clear. Tracing a substance that seems present everywhere, galaxies form and absent from nearly every detector built to find it. The mystery becomes narrower, but also deeper. The more ordinary explanations disappear, the more the hidden mass begins to look like a new part of nature, rather than an unseen corner of the old one. Once ordinary matter, antimatter, familiar neutrinos, and most compact objects are set aside, the search for dark matter enters a region where no confirmed particle has yet been found. The missing mass may consist of something entirely new, a form of matter that carries mass and responds to gravity, but remains almost invisible to every other force. This possibility is not added merely to preserve a convenient theory. The known inventory of particles is already understood to be incomplete, and dark matter may belong to a larger framework that has not yet been uncovered. The difficulty is that many possible particles could produce the required cosmic behavior, while each may leave only the faintest trace in a detector. One long-studied idea involves weakly interacting massive particles. These hypothetical particles would have much greater mass than a neutrino, and would interact through gravity and perhaps through the weak nuclear force. In the early universe, they could have been created in enormous numbers while matter and radiation remained extremely hot. As the universe cooled, most pairs would annihilate, but a small surviving population could remain. Under certain conditions, the predicted abundance approaches the amount of dark matter inferred today, giving the idea much of its historical strength. Yet appeal is not evidence. Decades of increasingly sensitive searches have not produced a confirmed detection. The candidate remains possible in some forms, but many of its simplest versions face strong constraints. Direct detection experiments attempt to observe a dark matter particle striking an atomic nucleus or an electron. The expected events are extraordinarily rare. A detector may contain a large mass of purified material and operate for months or years while searching for a few unusual flashes, charges, or vibrations. The experiment is commonly placed deep underground, where layers of rock absorb much of the cosmic radiation that would otherwise create false signals. Every component is chosen to minimize natural radioactivity. Shielding surrounds the target, yet ordinary particles still imitate the desired event. Neutrons can strike nuclei in ways that resemble dark matter. Radioactive decays can release energy at similar scales. The task is not simply to see a small signal, but to show that it cannot arise from anything already known. Liquid noble elements such as xenon or argon are often used because they can reveal a collision through both light and drifting electric charge. Other instruments register tiny deposits of heat or minute vibrations, with each design exploring a different range of masses and interactions. A heavy candidate may push a nucleus with a detectable recoil, while a much lighter particle may transfer so little energy that conventional detectors overlook it. The absence of a signal does not end the search. It narrows the allowed combinations of mass and interaction. Dark matter, if composed of these particles, must interact more weakly, possess a different mass, or behave in a less familiar way than many earlier models assumed. Indirect detection follows another path. If dark matter particles can annihilate with one another or decay over immense periods, they may produce ordinary particles such as gamma rays, neutrinos, electrons, or antimatter fragments. Dense regions should be the most promising places to look because more particles gather there. Galactic centers, dwarf galaxies, and the Sun are studied for possible excess signals. But these environments also contain violent ordinary processes. Pulsars, supernova remnants, black holes, and cosmic rays all produce confusing high-energy signals. A strange signal may be real without being dark matter. The challenge is to find a pattern with the correct energy, location, and intensity, one that appears across several instruments and cannot be explained by known astrophysics. So far, intriguing excesses appear from time to time, but none has become an accepted discovery. Collider experiments search in the opposite direction. Instead of waiting for dark matter from the galaxy to enter a detector, they collide known particles at high energies and look for something new to emerge. A dark particle would pass through the apparatus without leaving a direct track, but its absence could be inferred from missing energy and momentum. If the visible debris leaves with an imbalance, something unseen may have carried energy away, though the pattern must differ from familiar neutrino backgrounds. A discovery would require repeated events with properties matching a new particle. Even then, producing an invisible particle in a collider would not prove that it fills galactic halos. Its stability, abundance, and cosmic behavior would need separate confirmation. The strongest case would come from several directions at once: production in a collider, scattering in an underground detector, and a matching signal from space. Another major candidate is the axion, a hypothetical particle originally proposed to solve a problem in the theory of the strong nuclear force. Axions would be extremely light, electrically neutral, and produced in large numbers in the early universe. Although each particle would carry little mass, the immense population could supply the missing cosmic density. Axion dark matter would behave less like a swarm of isolated heavy particles and more like a coherent field spread across space. In a strong magnetic field, an axion might convert into a photon with a specific frequency. Experiments use resonant cavities, magnets, amplifiers, and other precision devices to search for this faint conversion. The search is technically difficult because the signal may be weaker than thermal noise and may appear only within a narrow frequency band. Researchers must tune instruments through many possibilities, listening across an unknown spectrum for a tone that may barely rise above silence. Even lighter candidates extend the field-like picture further. Ultralight dark matter could have wavelengths stretching across rooms, cities, or entire galaxies. Rather than arriving as individual impacts, it might cause tiny periodic changes in atomic clocks, interferometers, resonant sensors, or the behavior of fundamental constants. If the particle is light enough, quantum wave effects could alter the inner structure of small galaxies, smoothing regions that colder, heavier particles might leave dense. This offers a bridge between laboratory searches and astronomy. The shape of a dark matter halo can test particle properties, while a laboratory can search for the corresponding oscillation. Other theories propose sterile neutrinos, particles related to known neutrinos but even less interactive. Some suggest dark photons, hidden forces, or an entire dark sector containing several particles with their own interactions. Dark matter may not be a single featureless substance. It could possess complexity while remaining largely disconnected from ordinary matter. A dark sector might include stable particles, force carriers, and processes that shape halos in subtle ways. Such ideas are difficult to test, but observations of colliding clusters, dwarf galaxies, and halo structure can limit how strongly dark matter interacts with itself. Too much interaction would make halos rounder, produce drag in collisions, or alter the density at galactic centers. A small amount of interaction, however, might explain certain differences between simple cold dark matter simulations and observed galaxies. No single discrepancy yet demands this conclusion because ordinary gas, star formation, and stellar explosions also reshape galactic centers. The particle search therefore moves through a landscape of overlapping possibilities. Each experiment illuminates only part of it. A detector sensitive to heavy nuclear recoils may be nearly blind to an ultralight field. A telescope searching for annihilation radiation cannot test a perfectly stable particle that never self-destructs. A collider may create a candidate that was never abundant enough to dominate the cosmos. Negative results are meaningful, but they do not close every door. They carve away regions of possibility and force theories towards subtler interactions. The mystery survives not because it is immune to experiment, but because nature may have chosen a signal far below the range first expected. Still, dark matter cannot hide without limit. Its gravity is already measured, and any particle explanation must reproduce that cosmic role. It must remain stable for billions of years. It must be abundant enough to form halos. It must allow galaxies and the cosmic web to grow. It must avoid disrupting early element formation and the ancient background radiation. It must pass through ordinary matter with little effect, yet perhaps not with none at all. These demands create a narrow outline around an unknown identity. Somewhere within that outline may lie a particle that fills every galaxy, passes through every planet, and has so far touched human instruments only through gravity. The search continues in underground chambers, particle collisions, precision clocks, radio cavities, and maps of distant stars. Each method waits for a different whisper from the same unseen ocean. If one whisper becomes clear, the hidden scaffolding of the universe may finally acquire a name. The expanding universe does not announce itself as a wind rushing through space, or as galaxies flying outward from a single central point. It appears instead through a gradual change in light, a stretching of wavelengths that grows with distance and records the changing scale of space itself. For most of human history, the night sky seems fixed. Stars rise and set, planets wander against the background constellations, and comets occasionally cross the darkness. But the larger arrangement appears permanent. Even after telescopes reveal that the Milky Way contains vast numbers of stars, the wider universe remains uncertain. Some faint spiral objects are thought to be clouds within the galaxy, while others suspect that they are distant star systems in their own right. The question is settled only when their distances become measurable. Certain variable stars brighten and fade in regular patterns, allowing their true luminosity to be estimated. By comparing that intrinsic brightness with how faint they appear, astronomers determine that some spiral nebulae lie far beyond the Milky Way. The universe suddenly becomes much larger, filled with separate galaxies scattered across immense distances. Once those distances are known, another pattern emerges from their light. The spectra of galaxies contain familiar lines produced by atoms, hydrogen, calcium, oxygen, and other elements absorb or emit light at precise wavelengths, creating a kind of physical signature. In distant galaxies, many of these lines appear shifted toward longer, redder wavelengths. The effect is called redshift. Motion can cause such a shift. When a source moves away, successive waves arrive more spread out. much as sound waves from a receding object reach a listener at a lower pitch. Yet the galactic redshift is not only the ordinary motion of objects through a static emptiness. On the largest scales, it reflects the expansion of space between galaxies. The light begins its journey with one wavelength and travels across a universe whose scale continues to grow. As space stretches, the wavelength stretches with it. A photon arriving after a long cosmic journey carries the record of that expansion in its altered color. The farther the galaxy, the longer the light has traveled and the more expansion it has experienced. This produces the broad relationship associated with Edwin Hubble and earlier theoretical work. Distant galaxies generally recede faster than nearby ones. The pattern is not perfectly neat because galaxies also possess local motions. They orbit inside groups, fall toward clusters, and respond to nearby concentrations of mass. The Milky Way and the Andromeda Galaxy, for example, approach one another because their mutual gravity overcomes cosmic expansion across their relatively small separation. But when observations extend to sufficiently large distances, local motions become minor variations within a clear overall trend. Galaxies are separating because the space between unbound systems increases over time. This does not mean that expansion begins at a privileged center. Every large region sees distant galaxies receding in a similar way. A useful comparison is a pattern drawn on a surface that expands uniformly. Each mark becomes farther from every other mark without any mark serving as the center of expansion within that surface. The universe is not literally such a surface, and it does not need to expand into an external emptiness. The comparison only captures the way distances can grow everywhere at once. Space itself is part of the physical system. Its geometry changes with time. This idea follows naturally from general relativity, in which gravity is not a force acting across a rigid stage, but the behavior of space-time shaped by matter and energy. The equations allow the universe to expand or contract. A perfectly static cosmos requires a delicate balance and is not the generic outcome. Long before the expanding pattern is firmly observed, theoretical models already suggest that cosmic space may be dynamic. Observation then turns that possibility into a central fact. The expansion changes the interpretation of distance. A galaxy may recede from the Milky Way without moving through its immediate surroundings at the full recession speed assigned to it. Much of the growing separation comes from the increasing scale of the intervening space. Over modest distances, recession speeds are far below the speed of light. Across extreme distances, the accumulated expansion of space can make the separation grow faster than light without violating relativity, because relativity limits local motion through space, not the global growth of distance caused by changing geometry. This distinction becomes important when the observable universe is considered. Light from very remote galaxies may begin its journey when those galaxies are much closer than they are now. During the journey, expansion increases the distance the light must cross. Some regions visible today have since receded so far that signals emitted now may never reach the Milky Way. The observable universe is therefore shaped not only by the age of cosmic history, but by the rate at which space expands. Expansion also explains why looking far away means looking into the past. Light travels at a finite speed. The sun is seen as it was minutes earlier, nearby stars as they were years earlier, and distant galaxies as they were millions or billions of years earlier. A deep astronomical image is not a snapshot of one universal present. It is a layered record of different times. The most distant galaxies appear in younger stages because their light begins traveling when the universe itself is young. By measuring redshift, astronomers arrange these galaxies along a broad cosmic timeline. Small redshifts usually correspond to relatively nearby systems, while larger redshifts reveal earlier eras when the universe is denser and galaxies are less mature. The stretching of light becomes both a measure of expansion and a means of reconstructing cosmic history. Evidence for an expanding past appears in more than galactic redshifts. If the universe is expanding now, then reversing that expansion leads toward a hotter and denser state. The cosmic microwave background preserves radiation from such a state. It fills the sky with an almost uniform glow that has cooled and stretched as the universe grows. Its wavelengths are now far longer than those of the hot light that originally fills the young cosmos. The abundance of light elements also fits a period when matter is dense and hot enough for early nuclear reactions. Together, these records support a universe that evolves from a compact, energetic beginning rather than one that remains eternal and unchanging in its large-scale form. Expansion does not pull apart everything. Gravitationally bound systems resist it. Stars hold planets, galaxies hold stars, and clusters may hold groups of galaxies. Electromagnetic forces bind atoms and solid matter far more strongly than cosmic expansion acts across such small scales. A stone does not grow, a planet does not swell, and the distance between neighboring atoms does not increase with the universe. Expansion becomes important where matter is spread thinly and large structures are not tightly bound. Between distant galaxy groups, there is enough open space for the cosmic scale to dominate. The universe grows mainly through its broadest separations, while local islands of matter remain intact. This creates a layered cosmos. Within galaxies, gravity organizes stars. Between nearby galaxies, mutual attraction may govern motion. Across the largest distances, expansion prevails. The relation between distance and recession also provides a practical measure of the present expansion rate, though determining that rate precisely remains difficult. Different methods use nearby calibrated stars, exploding white dwarfs, ancient background radiation, or patterns in the distribution of galaxies. Their results do not align perfectly, suggesting either hidden measurement effects or physics not yet included in the standard picture. Even the basic pace of expansion therefore retains a quiet uncertainty beneath its broad certainty. For a time, many scientists expect gravity to gradually slow this expansion. Matter attracts matter, and the combined pull of galaxies, gas, and dark matter should resist the growth of distance. The universe may continue expanding forever at an ever-decreasing rate, or it may contain enough matter to halt and reverse the process. These possibilities make expansion seem like a motion launched by the early universe and then weakened by gravity. The central question appears to be how rapidly the expansion is slowing. Yet the answer that eventually emerges is not a simple measure of deceleration. Distant stellar explosions reveal that the expansion history bends in an unexpected direction. The universe is not merely continuing to expand. During its later history, the expansion begins to accelerate. That discovery transforms redshift from evidence of a growing cosmos into the entrance to a deeper mystery. The stretching of light first shows that space changes. The changing rate of that stretching then suggests that something within the universe, perhaps within empty space itself, is driving the largest structures apart with increasing speed. For most of the 20th century, cosmic expansion appears to be a contest between an ancient outward motion and the inward pull of gravity. The universe expands, but every galaxy, cloud, and dark matter halo adds attraction to the whole. Gravity should gradually reduce the rate at which large distances grow. The main uncertainty seems to concern how strong that braking effect might be. If the universe contains enough matter, expansion could eventually stop and reverse. If it contains less, expansion could continue forever while steadily slowing. In either case, Acceleration seems unlikely. The turning point comes from an effort to measure that slowdown directly. Astronomers need objects whose true brightness can be estimated, because apparent brightness alone does not reveal distance. A nearby dim object and a distant brilliant one may look equally faint. Certain stellar explosions provide a solution. A type of supernova produced when a white dwarf undergoes a catastrophic thermonuclear disruption can reach a remarkably consistent peak. Luminosity, once details of its light curve are corrected. These explosions become standardizable candles, objects whose observed brightness allows their distance to be inferred. Because they can be seen across billions of light years, they trace the expansion of the universe far into the past. Their redshifts reveal how much space stretches while their light travels, and their brightness reveals how far away they are. By comparing the two, the history of cosmic expansion can be reconstructed. The expectation is straightforward. If gravity has been slowing the universe, distant supernovae should appear at distances consistent with a faster expansion long ago and a slower expansion now. Instead, the explosions appear dimmer than expected. They are farther away than a decelerating universe predicts. The result does not fit the simple picture of expansion gradually losing momentum. The most natural interpretation is that expansion has sped up during the later history of the cosmos. Two independent research teams reached this conclusion near the end of the 20th century, and the finding is soon tested through additional observations. Dust may absorb some of the light, the explosions may change across cosmic time, calibration errors may affect the measured brightness. Astronomers compare many events, study their colors and spectra, and combine them with other records of cosmic geometry. As the data improve, the accelerating pattern remains. The discovery changes the central question of cosmology. The universe is not simply expanding despite gravity. Something appears to be driving the expansion against the collective attraction of matter. Acceleration does not mean that every galaxy suddenly begins moving through space like an engine gaining speed. It means that the scale factor of the universe, the quantity describing how large cosmic separations become, curves upward with time. Unbound regions grow apart at an increasing rate. A galaxy at a fixed co-moving position remains part of the large-scale flow, while the distance between it and other distant galaxies increases more rapidly as the universe evolves. The cause is given the name dark energy. Like dark matter, the name describes an effect rather than an identity. Dark matter attracts and gathers. Dark energy appears smooth and acts on the expansion of space. Dark matter helps build structure. Dark energy increasingly separates the largest unbound structures. They are grouped together because both are unseen and inferred indirectly, but their cosmic roles are almost opposite. One deepens gravitational wells, while the other dominates the geometry of the expanding universe. The transition from slowing to accelerating expansion occurs only after cosmic history has already unfolded for billions of years. In the early universe, matter is much denser because the same amount is packed into a smaller volume. Its gravitational influence dominates the large-scale dynamics, and expansion slows. As space grows, the density of ordinary matter and dark matter decreases. The particles become more widely separated. If dark energy is associated with a constant energy density of empty space, its density does not thin out in the same way. A larger universe contains more space, and therefore more total dark energy, even though its density remains constant. Eventually, the matter density falls below the dark energy density. At that point, the expansion begins to accelerate. Its relative importance grows because matter becomes increasingly dilute. The timing of this transition is itself puzzling. Cosmic history spans an immense interval. Yet the era in which matter and dark energy have comparable densities is relatively narrow. Human observers arise during this interval, when both influences can be measured. Selection effects may matter, because galaxies, stars, planets, and life require an earlier era in which matter can gather before acceleration dominates. Even so, the near balance between the two components remains a notable coincidence in the standard cosmological picture. Acceleration is supported by more than supernovae. The cosmic microwave background records the geometry and contents of the young universe. Patterns in the distribution of galaxies preserve a preferred scale created by sound waves in the early cosmic plasma. This scale acts as a standard ruler that can be measured at different times. The growth of galaxy clusters and the weak lensing of distant light also depend on the competition between gravity and expansion. When these observations are combined, a consistent model emerges in which ordinary matter is a small fraction. Dark matter forms most of the gravitating matter, and dark energy dominates the present energy density. The strength comes from several independent records agreeing on the same broad history. Yet agreement about the effect does not settle its cause. General relativity connects the contents of the universe with the behavior of space-time. Certain forms of energy can produce negative pressure, a property that allows accelerated expansion. Pressure in relativity contributes to gravity, but sufficiently negative pressure changes the sign of the large-scale effect. Instead of slowing expansion, it drives acceleration. The simplest form is a cosmological constant, represented as a fixed property of space-time. Its energy density remains unchanged as the universe expands. This model fits observations well, but the physical meaning of the constant remains obscure. Quantum theory suggests that empty space should possess vacuum energy, yet straightforward estimates are wildly different from the small value inferred from cosmology. The disagreement is so large that it cannot be treated as a minor error. It points toward a missing principle in the relationship between gravity and quantum physics. Other explanations propose a field that changes over time, allowing dark energy to evolve. Such a field might resemble other fields in physics while carrying an unusual pressure. If its strength varies, the future expansion could differ from the prediction of a cosmological constant. Measurements, therefore, seek the equation of state of dark energy, a relation describing its pressure compared with its energy density. A value matching a cosmological constant remains consistent with current evidence, but small deviations would transform the interpretation. Detecting such a deviation requires extremely precise maps of distance, structure, and lensing across vast portions of the sky. There is also the possibility that acceleration does not come from a new energy component. General relativity may need modification on the larger scales. A theory that behaves correctly around planets, stars, and galaxies could still differ across cosmic distances. Such a change would have to reproduce the observed expansion while also matching gravitational lensing, the cosmic background, the motion of galaxies, and the growth of structure. This is difficult because general relativity succeeds across many tests. Still, the scale of the mystery keeps modified gravity under consideration. The choice is profound. Either the universe contains an unknown component with unusual pressure, or the theory describing gravity is incomplete across the largest possible domain. The future consequences depend on which explanation is correct and whether dark energy remains constant. If acceleration continues at roughly its present character, distant galaxies beyond the local gravitationally bound region will recede ever faster. Their light will become increasingly redshifted and faint over immense time. Many will pass beyond a horizon from which newly emitted signals can never arrive. The observable cosmos available to future civilizations would grow darker and emptier, even though the universe itself continues to expand. If dark energy weakens, acceleration might slow. If it changes sign, cosmic contraction could become possible. If it grows stronger, it might eventually overcome structures at progressively smaller scales. These alternatives remain speculative because the measured behavior is still close to the simplest constant model. The immediate lesson is more restrained. Space is not a passive container. Its large-scale evolution responds to forms of matter and energy, including a dominant component whose nature is unknown. The faintness of distant stellar explosions reveals that the universe has crossed from deceleration into acceleration. A small shift in expected brightness opens a vast conceptual gap. Gravity no longer tells the whole story of cosmic expansion. Something smooth, persistent, and invisible has become the leading influence on the future geometry of the universe. Empty space appears simple only from a distance. Between galaxies there may be almost no stars, little gas, and scarcely any dust. Yet physics does not describe such regions as perfect nothingness. Space has geometry, fields can extend through it, and quantum theory allows activity even where no ordinary particles remain. Dark energy may arise from this hidden structure of the vacuum. In the simplest cosmological model, empty space possesses a constant energy density. As the universe expands and more space comes into existence, the amount of this energy increases in proportion to the growing volume, while its density remains unchanged. Matter behaves differently. A fixed collection of particles becomes more dilute as space grows, so its average density falls. Radiation thins even faster because its photons spread out and their wavelengths stretch. Vacuum energy does not fade in the same way. This difference allows it to begin as a minor influence and later become dominant. During the early universe, matter and radiation control cosmic behavior because they are packed densely together. Gravity slows the expansion and amplifies small variations into galaxies and clusters. Over billions of years, expansion reduces the density of matter. If the vacuum retains a constant energy density, it eventually outweighs the increasingly sparse contents of the cosmos. Once that threshold is crossed, accelerated expansion begins. This idea is expressed mathematically through the cosmological constant, a term that can be included in the equations of general relativity. It acts uniformly across space and time, not as a conventional force pushing galaxies from behind, but as a property affecting how space-time evolves. The effect becomes important only across enormous distances where local gravitational binding is weak. Within atoms, planets, solar systems, and galaxies, stronger forces hold structures together. Between distant unbound galaxy groups, the influence accumulates across vast regions and changes the expansion of the universe as a whole. The cosmological constant has a complicated history. It is introduced during an early attempt to describe a static universe. General relativity naturally permits expansion or contraction, so a constant term can be used to balance the attraction of matter and hold the cosmic scale steady. Once expansion is observed, this original motivation disappears. The term remains mathematically available, but for many years it seems unnecessary or artificial. The discovery of acceleration gives it a new role. Instead of preventing expansion, it can explain why expansion speeds up. The same mathematical ingredient returns with a different physical meaning, now interpreted as an energy of empty space, observationally. This simple model works remarkably well. A constant vacuum energy fits supernova distances, the cosmic microwave background, the distribution of galaxies, and measurements of large-scale structure with impressive consistency. Yet its success creates one of the deepest problems in modern physics. Quantum field theory also suggests that empty space contains energy. In that theory, Each field possesses a lowest possible state, but lowest does not necessarily mean zero. Even in a vacuum, quantum fields retain fluctuations. They cannot remain perfectly motionless because quantum uncertainty prevents exact stillness. These fluctuations are not ordinary particles permanently filling space, though they are sometimes described through the temporary appearance and disappearance of particle pairs. That picture is useful only as a loose image. More precisely, the vacuum is the ground state of interacting fields, and it carries measurable consequences. Effects such as small shifts in atomic energy and forces between closely spaced surfaces show that the quantum vacuum is not physically irrelevant. It is natural to ask whether the same vacuum energy could be the source of cosmic acceleration. The difficulty is scale. Straightforward estimates of quantum vacuum energy produce a value enormously larger than the density inferred from cosmology. Depending on how the calculation is framed, the mismatch can reach an almost unimaginable number of orders of magnitude. If the larger theoretical value gravitated in the ordinary way, space would expand so violently that stars, galaxies, and perhaps even stable atoms could never form. Yet the observed acceleration is gentle on local scales and becomes significant only across the largest cosmic distances. Something therefore cancels, suppresses, or transforms most of the expected vacuum energy. No accepted theory explains why the remainder is so small while not being exactly zero. This is known as the cosmological constant problem, and it exposes a major gap between quantum physics and gravity. Quantum field theory describes particles and forces with extraordinary accuracy, while general relativity describes gravity and space-time. Both theories succeed in their proper domains, but vacuum energy lies at their intersection. Quantum theory assigns structure to empty space, and gravity should respond to all forms of energy. The fact that the predicted and observed values disagree so dramatically suggests that the connection is not understood. Perhaps absolute vacuum energy does not gravitate in the expected way. Perhaps an unknown symmetry cancels most contributions. Perhaps the cosmological constant is not vacuum energy at all, but a separate fundamental quantity built into space-time. Each possibility preserves part of the picture while leaving another part unexplained. The language of space creating more space can also be misleading if taken too literally. Expansion is not a substance manufacturing new units of emptiness at a boundary. There is no visible edge where fresh space enters. Instead, the distance described by the cosmic geometry increases between unbound regions everywhere. If vacuum energy remains constant per unit volume, a larger volume contains more total energy. This does not violate ordinary energy conservation in the simple way it might seem, because energy conservation in an expanding universe is subtler than in a fixed background. General relativity guarantees local conservation, but a single conserved total energy for the entire evolving universe may not be well defined. The growth of vacuum energy is therefore tied to the changing geometry itself. Pressure is central to this behavior. In everyday experience, positive pressure pushes outward from within a gas. Yet in general, relativity pressure contributes to gravity. Ordinary positive pressure strengthens gravitational attraction on cosmic scales. Vacuum energy has negative pressure. As space expands, the energy density remains constant, and the effective pressure is sufficiently negative to produce acceleration. This does not mean that galaxies feel a local wind or that empty space pulls them apart directly. The negative pressure changes the large-scale evolution of the metric, the mathematical description of distances and time. Bound systems remain intact because their internal forces overwhelm the tiny cosmological effect. Only across immense unbound separations does the accelerated growth become apparent. The constancy of vacuum energy leads to a specific prediction, its equation of state, The ratio between pressure and energy density should remain fixed at the value associated with a cosmological constant. Observational programs measure the expansion history and the growth of structure to test this. If the value differs even slightly or changes with time, dark energy may be dynamic rather than constant. Such a discovery would point beyond a simple vacuum term toward a new field or a modification of gravity. So far, the cosmological constant remains consistent with the broad evidence, but precision continues to improve. Maps of galaxies, gravitational lensing, supernovae, and ancient radiation are being compared across cosmic time, searching for a small departure that may reveal the nature of the hidden component. Empty space may therefore be the most energetic substance in the universe, but only in a quiet and distributed sense. A small volume contains almost none of the dark energy needed to produce a noticeable effect. Across the enormous volume between galaxy clusters, the total becomes dominant. The contrast is profound. Stars release tremendous energy in compact regions. Black holes reshape their surroundings, and galaxies carry vast stores of mass. Yet the smooth vacuum outweighs them collectively because space is so abundant. Its power comes not from intensity but from extent. Every newly expanded region contributes the same faint density, and the sum grows as the cosmos enlarges. This possibility changes the meaning of emptiness. The vacuum is no longer merely the absence of matter. It becomes a physical state with properties that shape the fate of the universe. Yet the name dark energy still conceals more than it explains. The measured acceleration may be consistent with vacuum energy, but consistency is not identity. Until the cosmological constant is understood, or until a different behavior is detected, empty space remains both the simplest answer and one of the deepest mysteries. The universe may be driven apart by the quiet energy of nothing, while physics still struggles to explain why nothing carries exactly the amount required. The simplest explanation for dark energy is also the most difficult to understand. A cosmological constant fits the observed acceleration with remarkable economy. It requires no new particle moving through space, no field changing over time, and no complex interaction with ordinary matter. It treats the energy density of empty space as fixed, uniform, and present everywhere. In general relativity, this constant changes the large-scale behavior of space-time and allows expansion to accelerate. Observations remain broadly consistent with this picture, yet the theory gives no satisfying reason for the constant to possess its measured value. It is small enough to permit galaxies, stars, and life to form, but large enough to dominate the universe during its later history. A number written into space-time can describe the effect, but description is not explanation. The puzzle deepens because quantum physics also assigns energy to the vacuum. Every known field contributes something to its lowest energy state. Straightforward estimates do not resemble the mild dark energy density inferred from cosmic expansion. They are vastly larger. Some unknown cancellation must remove almost all of this energy while leaving a tiny remainder. No established principle explains why this cancellation should be so precise or why it should stop just short of zero. The cosmological constant therefore appears mathematically simple and physically mysterious. It may be a fundamental property of nature, but it may also be a placeholder for a deeper mechanism. One alternative proposes that dark energy is not constant at all. It may be produced by a dynamic field spread throughout the universe. Such a field is often called quintessence, a name suggesting a fifth cosmic substance beyond ordinary matter, radiation, dark matter, and the vacuum constant. Like other fields in physics, it would possess an energy density determined by its state. Unlike the fixed cosmological constant, that state could evolve. The field might roll slowly through an energy landscape, changing its strength over billions of years and altering the rate of cosmic acceleration. In the present era, it could imitate a cosmological constant closely enough to match existing measurements, while still carrying subtle variation. This possibility would transform dark energy from a permanent property of space into a process unfolding through cosmic time. A dynamic field offers flexibility, but that flexibility creates new questions. Its mass would need to be extraordinarily small so that it changes only over immense timescales. It would need to remain smooth across vast distances rather than gathering into galaxies as matter does. It would also need to avoid producing detectable forces or changes in particle behavior. Precision experiments already place strict limits on unexplained long-range forces and on variations in fundamental constants. Quintessence must therefore be active enough to accelerate the universe, but quiet enough to remain hidden everywhere else. If the field rolls too quickly, dark energy changes more than observations allow. If it barely moves, it becomes almost indistinguishable from the cosmological constant it was meant to replace. Another family of ideas allows the dark energy density to behave even more strangely. Its pressure may be more negative than that of a cosmological constant, causing the density itself to increase as the universe expands. This hypothetical form is sometimes called phantom energy. If it persists, acceleration grows without limit. Over an immense future, galaxy clusters separate. Galaxies lose their outer stars. Planetary systems become unbound, and eventually even atoms may be torn apart. This outcome, often called a big rip, is not required by current evidence. Measurements remain compatible with a constant density, and phantom theories can suffer from deep instabilities. More sophisticated models attempt to avoid these problems, but the idea remains speculative. Its value lies partly in showing how strongly the future depends on the exact properties of dark energy. Other proposals allow the field to weaken, reverse, or interact with dark matter. If dark energy slowly decays, acceleration could eventually end. Matter might regain influence, and expansion could return to a gentler pace. If the effective energy becomes negative, gravity could halt expansion and draw the universe into contraction. An interaction between dark energy and dark matter could change how both components evolve, perhaps explaining why their densities become comparable during the current era. Yet any exchange would alter the growth of galaxies, the motion of clusters, and the ancient background radiation. The interaction must be weak or carefully structured to escape existing limits. These models offer possible solutions to the coincidence problem. The question of why dark matter and dark energy possess similar cosmic densities only during a relatively brief period. Still, they often replace one unexplained number with several new parameters. A different path questions whether dark energy exists as a substance at all. General relativity may be incomplete on the larger scales. The theory is tested with extraordinary precision within the solar system, around stars, through binary motion, and through gravitational waves. Yet cosmic acceleration operates across distances far beyond those direct tests. Gravity could change subtly when fields become extremely weak, or when distances become immense. Modified gravity theories attempt to reproduce acceleration through altered equations rather than an added energy component. Some introduce extra fields, additional geometric terms, or hidden dimensions. Others propose that gravity leaks into unseen directions across large scales, weakening its attractive effect and allowing expansion to speed up. These ideas must satisfy demanding conditions. They must behave almost exactly like general relativity wherever the theory is already confirmed. They must produce the correct expansion history, match gravitational lensing, and reproduce the growth of cosmic structure. A model that fits supernova distances but predicts the wrong pattern of galaxy clustering cannot succeed. Many modified theories can imitate dark energy in the background expansion, but they often differ in how gravity gathers matter. This gives observations a way to distinguish them. Surveys compare cosmic geometry with the rate at which galaxies and clusters form. If expansion and structure growth require inconsistent amounts of dark energy under general relativity, the mismatch may point toward modified gravity. So far, the standard model remains broadly successful, though uncertainties leave room for alternatives. There is also the possibility that apparent acceleration arises from the uneven structure of the universe rather than a new component or law. Matter gathers into galaxies, clusters, filaments, and walls, leaving large voids between them. Standard models average this complexity into a smooth background. Some researchers investigate whether inhomogeneity, sometimes called back reaction, could alter the average expansion enough to mimic acceleration. Others consider whether the Milky Way lies within an unusually large underdense region. These ideas face strong constraints. The cosmic microwave background is highly uniform. Large surveys do not support a local void extreme enough to explain the full acceleration, and most analyses find back reaction insufficient as a complete replacement. Even so, the question tests how accurately a lumpy universe can be represented by smooth equations. Every candidate explanation must confront the same set of observations. Supernovae trace distance through stellar explosions. Patterns left by ancient sound waves provide a cosmic ruler. The microwave background records the young universe. Weak gravitational lensing maps total matter. While galaxy clustering reveals how structure grows, no single method can identify dark energy by itself. The power comes from comparing them across different eras and physical effects. A cosmological constant predicts one history. A rolling field predicts another. Modified gravity may preserve expansion while changing structure formation. Future measurements seek tiny differences among these possibilities. They ask whether acceleration changes, whether gravity behaves normally across cosmic scales, and whether dark energy varies in space or time. The difficulty is that the simplest model already fits so well. Any deviation may be small, requiring enormous surveys, precise calibration, and careful control of error. A slight bias in supernova brightness, galaxy shape, or distance measurement can resemble new physics. The hidden component is smooth, faint in its local effects, and revealed only through the accumulated behavior of the universe. For now, several explanations remain open, but they do not stand on equal footing. The cosmological constant is the leading description because it requires the fewest assumptions and matches the broad evidence. Dynamic fields remain possible, because measurements cannot yet prove perfect constancy. Modified gravity remains possible, because cosmic distances probe a regime beyond direct local tests. More exotic models survive only within narrower boundaries. The mystery persists not because there are no ideas, but because different ideas can produce almost the same visible universe. Each reproduces acceleration while hiding its differences in effects that are difficult to measure. Dark energy may be a number, a field, a failure of gravity, or a sign that empty space has properties not yet understood. Every path leads toward the same deeper question. Why does the universe contain a smooth influence that begins to dominate only after galaxies have formed? Until that question is answered, cosmic acceleration remains both a measured fact and an unresolved interpretation. The visible universe is bright enough to suggest completeness. Galaxies fill deep images with spirals, ellipses, collisions, and clusters. Stars reveal their temperatures through color, their motion through shifted spectra, and their age through the chemistry carried in their light. Planets form from disks of dust and gas, atoms combine into molecules, and simple elements become complex worlds. Across this illuminated landscape, science measures distance, mass, time, composition, and motion with growing precision. Yet the broad cosmic account remains dominated by two components that have never been directly identified. Dark matter supplies most of the gravitating matter, shaping galaxies and the web that connects them. Dark energy supplies most of the total cosmic energy density, governing the accelerated expansion of space. Together they form nearly all of the universe, while ordinary matter forms the small remainder from which every telescope, laboratory, and observer is built. This contrast reveals the difference between describing behavior and understanding substance. The universe can be modeled with impressive accuracy, even when its main ingredients remain unknown. Measurements of the cosmic microwave background, galaxy clustering, gravitational lensing, stellar explosions, and orbital motion fit a common framework. Within that framework, dark matter is cold enough to gather, stable enough to survive across cosmic time, and quiet enough to avoid strong interactions with light. Dark energy is smooth enough to remain nearly uniform, persistent enough to dominate at late times, and unusual enough to drive acceleration rather than collapse. These properties describe what the hidden components must do. They do not reveal what they are. Dark matter may be a particle beyond the known families of matter. It may be an ultralight field, a heavier weakly interacting particle, a collection of hidden species, or a more complicated dark sector. Some fraction may reside in primordial black holes or other compact objects, though observations restrict how much. It may interact with itself weakly, leaving subtle effects in the centers of galaxies and during cluster collisions. It may pass through ordinary matter almost entirely untouched, even while vast numbers of its particles move through planets and stars. Each possibility offers a different experimental path, yet none has become a confirmed identity. Dark energy is even less tangible. It may be the vacuum energy of space, represented by a cosmological constant. It may be a field that evolves so slowly that it appears nearly fixed. It may signal that gravity changes across the largest distances, or that the relation between quantum physics and space-time is missing a fundamental principle. The observations define a smooth influence on expansion, but they do not reveal a particle to capture or a local source to isolate. Dark energy becomes known through the history of distance itself. Its laboratory is the universe as a whole. The two mysteries are therefore different in method as well as effect. Dark matter gathers around galaxies and clusters, allowing its distribution to be mapped through motion and lensing. It leaves structure. Dark energy appears not as a clump but as a background influence, detected through the changing rate at which unbound regions separate. It alters geometry. Dark matter becomes relatively less important as the universe expands and its average density falls. Dark energy becomes relatively more important if its density remains constant. One builds the places where stars can form. The other increasingly isolates those places from one another. Cosmic history unfolds between their competing effects. In the early universe, radiation dominates. Later, matter takes control, and dark matter guides the growth of large structure. Still later, dark energy overtakes matter and turns deceleration into acceleration. Ordinary matter creates the visible detail within this changing balance, cooling into galaxies, igniting into stars, and assembling into planets. The familiar cosmos emerges as a luminous response to forces and substances that remain mostly hidden. Dark matter and dark energy are sometimes treated as proof that cosmology is built on guesses. The opposite is closer to the truth. Their existence is inferred because independent observations repeatedly fail in the same direction when only visible matter is included. Galaxies rotate too quickly. Clusters bend too much light. Structure grows too efficiently. Distant supernovae appear too faint for a slowing universe. Ancient radiation preserves a balance of components that ordinary matter alone cannot reproduce. The names remain provisional, but the effects are not arbitrary. They are supported by patterns that cross different instruments, wavelengths, distances, and errors. A future theory may change the interpretation, but it must still explain those patterns. It cannot simply remove the darkness by renaming it. Any replacement must account for the motions of stars, the lensing of clusters, the formation of the cosmic web, the geometry of the early universe, and the late acceleration of expansion with equal or greater success. This demand gives the mystery a firm boundary. The unknown is not shapeless. It is surrounded by evidence. Experiments continue to press against that boundary. Underground detectors search for rare collisions. Resonant cavities listen for faint conversions of axions into light. Precision sensors look for oscillating fields. Particle colliders search for missing energy carried by invisible products. Telescopes map dwarf galaxies, stellar streams, cluster mergers, and the weak distortion of distant galaxies. Large surveys measure redshifts and stellar explosions, tracing expansion across cosmic time. Each method tests a different part of the hidden framework. A discovery in one channel would need confirmation in others. A particle detected beneath a mountain must also behave correctly inside galaxies. A deviation in cosmic expansion must survive comparison with structure growth in the microwave background. The hidden universe will not be solved by a single dramatic image. It will be revealed through convergence, when several independent paths point toward the same underlying physics. The answer may also change the meaning of ordinary matter. If dark matter belongs to a hidden sector with its own forces, then the known particles may form only one branch of a larger material world. If dark energy arises from vacuum physics, then empty space may possess a structure more fundamental than particles themselves. If gravity must be modified, space-time may behave differently across scales too large for local intuition. Any of these outcomes would reshape the basic categories used to describe reality: matter, energy, emptiness, and geometry would no longer stand as separate ideas in their familiar forms. Their relationships would become part of a deeper theory. Yet the present uncertainty does not reduce the universe to confusion. It creates a disciplined openness. Some statements are secure. Galaxies require more gravity than their visible contents provide. Light bends around unseen mass. Large-scale structure grows within a dark framework, and cosmic expansion accelerates. Other statements remain conditional. The missing mass may be particulate. The acceleration may come from vacuum energy, and the simplest model may be only an approximation. Keeping those levels separate is essential. Mystery begins where evidence ends, not where evidence is ignored. The hidden universe invites speculation, but it also limits it. Every possibility must return to measurement. Human understanding occupies an unusual position within this cosmic account. The atoms that form instruments and minds are rare in the overall budget, yet they are capable of detecting the dominance of what they are not. Ordinary matter becomes arranged into observers able to infer invisible halos from stellar motion and the energy of empty space from the fading light of distant explosions. A small component of the universe learns that it is small. This realization is not a defeat. It is a measure of how far observation can reach beyond direct experience. The senses reveal surfaces, while science reconstructs hidden causes. Gravity exposes what light cannot. Time reveals what local experiments cannot. The cosmos becomes intelligible in layers, and each layer opens onto another unanswered question. Dark matter and dark energy may eventually receive precise identities, equations, and experimental signatures. They may prove to be separate pieces of a still larger theory, or they may show that the categories now used are incomplete. Until then, the universe remains mostly hidden without being silent. Stars orbit, galaxies cluster, light bends, and space expands. The evidence continues across the sky in patterns calm enough to overlook and persistent enough to transform physics. The visible fraction does not stand alone. It floats within an unseen architecture and an accelerating geometry, surrounded by realities known through their influence. The deeper picture remains unfinished, but its unfinished edges are already visible. Beyond every measured effect lies the possibility of a new substance, a new field, or a new understanding of space itself. The darkness is therefore not an empty absence at the edge of knowledge. It is the largest part of the universe, pressing quietly against everything that is known.